Hello, welcome to Chemical Kinetics. This will be part one. We're looking at first order reactions to start with. So let's just get an idea what kinetics is. Kinetics is the study of reaction rates. So in chemistry and biology as well, reactions flow at different rates, and changing the rate changes quite a lot of things. So in your body, for example, changing rates can mean the difference between different metabolisms needed for different amounts of time. If you have to burn more sugar or burn more oxygen for your body's needs, then you're going to have to change rates. Or if you eat food, you're going to have to change rates in order to digest that food. There's rates of reaction changes just involved in just simply thinking. So rate changes are widely important in the study of science. And so let's look at what we call first order rate laws. Now before we get into too much detail on what that means, first order versus second order versus third order, let's just go ahead and look at it mathematically and talk about it right here. The order of a reaction simply means that the effect of the change in the concentration affects the rate in a first order. So first order would be like to the first power. So if I double this change, it doubles that change. But you can also have second order, where if you double this change, it quadruples this change because it's now to the second power, and so on. And so typically we only have first and second order rate laws that we're going to look at and really have any calculations to do with. Your overall equation, though, you can add up if you have a first order reactant and a second order, and whatever, you can end up with a third order overall reaction. But analyzing this reaction right here, we're just looking at the reaction of A turning into B. And so, so let's take a look at this. When we talk about the rate in first order, we're saying that as the concentration of A decreases, so this negative change in A over time, that's what the rate equals. So the rate, it's like a speed. Chemical kinetics, it's like change in distance over time would be speed. So this is change in how quickly does this change into this. And so we have an amount of change, and then we have a time. And so we have like that. And so another way of expressing this would be equals a constant K times A. So we could have a mathematical constant that relates these things as well. And so we could solve for that constant. We can solve, or we can measure for the concentration of A. And this is what we call a differential rate law. So differential rate laws just simply express that the rate depends on the change of this concentration over time. I'll give you a graph that looks sort of like this. And so you could solve for these things instantaneously around here. Along this graph, if you were to graph it out, you could use that to solve. But we want a quicker way to solve things, a way we can just punch stuff into our calculator. And so what we do is we use calculus, and we integrate both sides of this equation through a process called integration, and we get what's called an integrated rate law. So the integrated rate law helps out because it'll relate the initial concentration, because we should know our starting concentration, and to any concentration at any time. And so this is how the integrated rate law is written. In order to use it, we say that the natural log of the concentration at some time, t, minus the natural log of the concentration at your starting time equals the negative constant times the time. And so rewriting it actually in this format right here, if you take it and rewrite in this format, actually tells you why this is so useful, because it actually gives you a y equals mx plus b linear equation, which is much easier to solve for things and make stuff more fluid. So our concentration at any given time, like let's say that this is our graph, so we have our concentration right there. So our concentration is going to be our y, and then our time is going to be our x. So time is down here on the graph. So we have a y and an x, and say, that makes a point. Well, then in this equation as well, we have the negative k, which is going to be our slope, and we have the b, which is going to be our y-intercept. So the y-intercept, of course, is the starting point. And so from the starting point and the slope, we can get a nice little linear line right there for a first-order reaction by using the integrated rate law. So it allows us to solve things. So let's go ahead and just punch some numbers into that and see if we can't solve this. All right, so let's say this is our data. Let's say that our concentration, we started with 2 molar, and we measured it 5 seconds later. So let's say this is time in seconds. So 5 seconds later, we were down to 1.6. And then 10 seconds after that, we were down to 1.2. So what's the value of K? We have everything else in here. And so let's go ahead and solve for the value of K. So we have the natural log of, oops, sorry, should be lowercase. We have the natural log of the starting, or the condition at time t. So let's just choose 1.6. We could use 1.2, but let's choose 1.6 for this particular time. And so of 1.6, natural log of 1.6 minus the natural log of our starting concentration. We know our starting concentrations at time 0 was 2. So 2 molar right there equals negative K. That we need to solve for, and this particular molarity was found at 5 seconds, so that's our time right there. So we plug all those values in, and then as you can see, this isn't so difficult to solve for. So the natural log here, if we sort of calculate this out, we're going to have negative 0.22 equals negative 5 times K. If we solve this, subtract it from this, we end up with negative 0.22 equals negative 5 times K. So divide negative 0.22 by negative 5, and we find that K equals 0.045. And the actual value of this for this particular first order reaction is going to be over seconds. Or you could say s to the negative 1. And we'll go over how to do that in a subsequent video. But that would be a simple way to use the integrated rate law to solve for a constant. And there's the integrated rate law and how you get it for a first order reaction.